myself, Dr. Raj Kishore Sharma. I'm working as an associate professor in chemistry department of Delhi University. Today we are going to discuss about the module Introduction of Raman Spectroscopy. This is under the paper of Surface Analytical Techniques 2. In introduction part, we will talk about the history of Raman spectroscopy and how it is originated. Then we will discuss the Raman scattering, characteristics of Raman scattering, advantage of Raman spectroscopy, comparison between Raman and IR. These are the topics we are going to cover. After the scattering, we will talk about the Raman depolarization and its rules, basic principles of Raman spectroscopy, and the classical treatment of Raman spectroscopy. The outlines of this presentation: number 1, a new type of secondary reaction; number 2, the Raman effect in inelastic scattering; 3, characteristics of Raman scattering; 4th, Raman spectroscopy and introduction, comparison of Raman and IR; the 5th is Raman spectroscopy and overview; 6th is intensity of Raman, normal Raman peaks; 7th is Raman depolarization ratios; the 8th point would be basic principle of Raman spectroscopy; 9th is resulting Raman spectroscopy; 10th is Raman spectroscopy, the classical treatment; and the last is advantages of Raman spectroscopy. A new type of secondary radiation. If we assume that X-ray scattering of the unmodified type observed by Professor Crompton corresponds to the normal or average state of the atoms and molecules, while the modified scattering of the altered wavelength corresponds to their fluctuations from that state, it would follow that we should expect also in case of ordinary light. In case of ordinary light, two types of scatterings. One determined by the normal optical properties of the atoms or molecules, and another representing the effect of their fluctuations from their normal state. It accordingly becomes necessary to test whether this is actually the case. Experiments have confirmed the anticipation and shown that in every case in which light is scattered by the molecules in dust-free liquids or gases, the diffuse radiation of the ordinary kind having the same wavelength as the incident beam is, as the incident beam is accompanied by a modified scattered radiation of degraded frequency. In experiments, a beam of sunlight is converged successfully by a telescopic object of 18 cm aperture and 230 cm focal length, and by a second lens was placed that on scattering material, which is either a liquid carefully purified by repeated distillation in vacuum, or it is dust-free vapor. To detect the presence of a modified scattered radiation, the method of complementary light filters is used. A blue-violet filter, when coupled with a yellow-green filter and placed in the incident light, it completely extinguished the track of the light through the liquid or vapor. The reappearance of the track when the yellow filter is transferred to a place between it and the observer's eye is the proof of the existence of a modified scattered radiation. Spectroscopic confirmation is also available. The investigation is naturally much more difficult in the case of gases and vapors, owing to the excessive feebleness of the effect. Nevertheless, when the vapor is of sufficient density, for example with ether or amylene, the modified scattering is readily demonstrable. Professor C.V. Raman. Professor C.V. Raman received Nobel Prize in Physics in 1930 for his work on the scattering of light and for the discovery of the effect named after him. Since the discovery of the Raman effect, or Raman spectroscopy has been a field of the real advances. In the recent years, the procedure was basically used to concentrate on vibrational conditions of basic atoms. This was because of the inaccessibility of serious monochromatic light sources and the absence of reasonable optical parts and identifiers. At the outset, the discovery of lasers in 1960 and the advancement of high throughput monochromators and sensitive detectors, Raman spectroscopy has been progressively more applied to solve problems of both technological as well as of fundamental interest. The Raman effect or inelastic scattering. When incident light is scattered from a crystal or molecule, most of the photons are elastically scattered. The scattered photons possesses same energy or same frequency and therefore wavelength as the incident photons. However, a small fraction of light, which is nearly 1 in 10 to the power 7 photons, gets scattered at optical frequencies different from and which is usually lower than the frequency of the incident photons. The process which leads to inelastic scatter is termed the Raman effect. Change in rotational, vibrational or electronic energy of a molecule can cause Raman scattering. Oppositely, if the scattering inelastic, the process is also known as Rayleigh scattering. Characteristics of Raman scattering. If the sample being studied is irradiated by monochromatic light, for example, a laser, the recorded spectrum of the scattered light consists of a strong line of the same frequency as the incident light and a weaker line on either side shifted from the strong line by frequencies ranging from a few to about 3500 centimeter inverse. Those lines of frequency which are less than the exciting lines are called Stokes lines, and the other lines are termed as anti-Stokes lines. They are very weak they have very weak signal effects. Only photon is Raman scattered. NIR elastic scattering in tissue. NIR absorption in tissues, red absorption in tissue or water, Raman scattering in tissue or water. True scattering process. Virtual state is a short-lived distortion of the electron cloud which creates molecular vibrations, and the order is tau is less than 10 to the power minus 14 seconds, which is a very short period. Strong Raman scatterers have distributed electron clouds, that C double bond C and pi bonds are the examples. Raman spectroscopy. Raman and mid-IR spectroscopy are complementary vibrational techniques, and normally both are necessary for completely vibrational profile of a testing molecule, although some vibrations may be active for both IR and Raman, but these two forms of spectroscopy arise from different methods and different selection principles. Usually, Raman spectroscopy is for symmetric vibrations in non-polar groups, while IR spectroscopy is best suited for the asymmetric vibrations of polar groups. Raman spectroscopy is complementary to IR spectroscopy. Radiation at a certain frequency is scattered by the molecule with shifts in the wavelength of the incident beam. The observed frequency shifts are related to vibrational changes in the molecule, which is associated with IR absorbance. Raman scattering spectrum resembles IR absorbance spectrum. Raman and IR mechanisms, however, differ. Now we will talk about the difference between IR and Raman scattering. On the left hand side you see the IR and on the right hand side you have Raman. Point number 1 is the vibrational modes. 2 is change in dipole moment. In IR, Raman both have vibrational modes. There is change in dipole in IR, however in Raman there is change in polarizability. Point 3 is excitation of molecules to excited vibrational states. However, in case of Raman, it is momentary distortion of the electrons distributed around the bond. Point 4 in IR is asymmetric vibrations. These are active, and in Raman these are symmetric vibrations. Those are active. An overview of Raman spectroscopy. IR and Raman are the most common vibrational spectroscopies for assessing molecular motion and fingerprinting species. Based on inelastic scattering of a monochromatic excitation source, minimal sample preparation. Sample could be a gas, liquid or a solid. So it is minimal sample preparation and it is compatible with wet samples and at normal ambients. Intensity of normal Raman peaks. The intensity or power of a normal Raman peak depends in a complex way upon the polarizability of the molecule, the intensity of the source and the concentration of the active group. The power of Raman emission increases with the fourth power of the frequency of the source. Raman intensities are usually directly proportional to the concentration of the active species. Raman depolarization ratios. Polarization is a property of a beam of radiation and describes the plane in which the radiation vibrates. Raman spectra are excited by plane polarized radiation. The scattered radiation is found to be polarized to various degrees depending upon the type of vibration responsible for the scattering. Experimentally, the depolarization ratio may be obtained by inserting a polarizer between the sample and the monochromator. The depolarization ratio is dependent upon the symmetry of the vibrations responsible for scattering. Now, polarized band. These are denoted by small p and they are lesser than 0.76 for totally symmetric modes, A 1G mode. Depolarized light, the p is equal to 0.76 for B1G and B2G non-symmetrical vibrational modes. Anonymously polarized bands, P is greater than 0.76 for A2G vibrational modes. Now, the basic principles of Raman spectroscopy. Light is scattered by the sample at various angles by momentary absorption of virtual state and re-emission. The Raman effect arises when a photon is interacted with the molecule and consequently interacts with the electric dipole of the molecule. According to the quantum mechanics, the scattering is denoted as an excitation of a virtual state with lower energy than a real electronic transition with nearly coincident de-excitation and change in vibrational energy. The scattering event occurs in about 10 to the power minus 14 seconds or less than that. The scattering virtual state description is shown in figure 1. The energy difference between the excitation and scattered photons is represented by the arrow of variable light in figure 1. Mathematically, the Raman shift recorded Raman shift is recorded in wave numbers, that is unit is centimeter inverse. At room temperature, the thermal percentage of vibrational excited states are low but not zero. Therefore, the initial state is called as ground state, and the scattered photon will have lower energy corresponding to the longer wavelength as compared to the exciting photons. This is the Stokes shifted scatter, which is usually observed in Raman spectroscopy as shown in figure 1. A small portion of the molecules are vibrationally excited states. Raman scattering from vibrationally excited molecules left the molecule in ground state. The scattered photons appear at higher energy state, which is shown in figure 1. The anti-Stokes shifted Raman spectroscopy is lower in weaker intensity, is always in weaker intensity than the Stokes shifted spectrum. While at room temperature, it is strong enough to be useful for vibrational frequencies. The range is less than 1500 centimeter inverse. Both Stokes and anti-Stokes spectral contains the same frequency information. The anti-Stokes spectrum could be employed when the Stokes spectrum is not directly observable. For example, because of poor response from detector at lower frequencies. There are two types of collisions that occur: elastic and inelastic. In case of elastic collision, it occurs between photons and molecules and results in no change in energy. However, the inelastic collision results in a net change in energy. The figure shows two types of Raman scattering. When a probe beam of radiation described by the electric field E interacts with a material, it induces a dipole moment mu in the molecule that compose the material. We can write mu is equal to A into E, where A is the polarizability of the molecule. The polarizability is a proportionality constant describing the deformability of the molecule. In order for a molecule to be Raman active, it must possess a molecular bond with a polarizability that varies as a function of interatomic distance. Light striking a molecule with such a bond can be absorbed and then re-emitted at a different frequency. We call it Raman shift, corresponding to the frequency of the vibrational mode of the bond. If molecule is in its ground state, upon interaction with the probe beam, the light can be absorbed and then re-emitted at a lower frequency, since energy of the light is channeled into the vibrational modes of the molecule. This is referred to as Stokes shifted Raman scattering. If molecule is in a vibrationally excited state when it interacts with the probe beam, the interaction can cause the molecule to give up its vibrational energy to the probe beam and drop to the ground state. In this case, the scattered light is higher in frequency, that is shorter wavelength than the probe beam. This is referred to as anti-Stokes Raman scattering, which under normal conditions is much less common than Stokes scattering. The most common occurrence is that light is absorbed and re-emitted at the same frequency. This is known as Rayleigh or elastic scattering. Both Rayleigh and Raman scattering are inefficient processes. Typically, only one part in 1,000 of the total intensity of incident light is Rayleigh scattered, while for Raman scattering, this value drops to 1 part in a million. Thus, a major challenge in Raman spectroscopy is to attenuate the light that is elastically scattered in order to detect the inelastically scattered Raman light. The resulting Raman spectrum is shown in figure. Lines in lower energy shifts are Stokes lines and lines in higher energy shift are anti-Stokes lines. The probability of emission and observed intensity is shown in a trend that the Rayleigh scattering occurs at much higher energy than Stokes and the anti-Stokes are at the much lesser energy. There is a difference in population of energy levels of vibrational transitions. Intensity of Raman lines are 0.001% of the intensity of the source. Number of peaks are related to degree of freedom. The degree of freedom, which we write capital D, O and capital F, degree of freedom DOF, is equal to 3 capital N minus 6 in band mode or 3n minus 5 in linear mode for n atoms. The selection rules related to the symmetry are, the rule of thumb is symmetric, it means it is Raman active. If it is asymmetric, it is IR active. Now look at the examples of CO2 and H2O, that is carbon dioxide and water molecule. These are the different modes of vibration in which some are only Raman active and some are both Raman and IR active. Active Raman vibrations. It needs change in polarizability for molecules during vibration. Polarizability related to electron cloud distribution. IR and Raman are complementary and can be cases where vibration is both IR and Raman active. The example is SO2, which is a non-linear molecule. In general, IR tends to emphasize polar functional groups, that is ROH or COOH, whereas Raman emphasizes on aromatic and carbon backbone, that is C double bond C, CH2, etc. Raman does not see many common polar solvents and can be used with aqueous samples. Now, the advantages of Raman spectroscopy. It provides molecular fingerprints of each analyte. It provides the possibility of highly selective determinations. It is applicable for any optically accessible sample, that is, it could be organic, inorganic or biological. Solid, liquid, gases, transparent and non-transparent samples can be measured. Aqueous solutions present no special technical problems and sample scanning is non-invasive. In qualitative information, what we get, number one, the characteristic regions for different groups as in IR. Number two, Raman correlation charts are available, so we can correlate the information we obtain in spectra and relate it. Number three, good for aqueous samples. The technique is good for aqueous samples. And in quantitative information, which is not routinely used, there are fewer technical problems than IR. There are few peaks, so interpretation is easy here. There is interference with fluorescence. The negative part is it has higher cost, signal is weak and require modified Raman methods. Resonance Raman spectroscopy allows detection of 10⁻³ to 10⁻⁷ molar using laser lights with wavelength approaching electronic absorption. Surface enhanced Raman spectroscopy places sample on metal or rough surface that increase the Raman scattering. Why Raman spectroscopy? Raman is a light scattering technique, so all that is required for the collection of a spectrum is to place the sample into the excitation beam and collect the scattered light. There are few concerns with sample thickness and little interference from the ambient atmosphere, so there is no need for high vacuum or desiccated sample holders. Glass, water and plastic packaging have weak Raman spectra, making the technique even easier to use. Samples usually can be analyzed directly inside a glass bottle or plastic bag without having to open the package and risk contamination. Aqueous samples are readily analyzed without having to remove water, and because there is no interference from ambient humidity, there is no need to purge the instrument. Now, no two molecules give exactly the same Raman spectrum, and the intensity of the scattered light is proportional to the amount of material present. Thus, Raman provides both qualitative and quantitative information about the sample, allowing the spectral interpretation. library searching, data manipulation, and the application of chemometric methods. Raman spectroscopy is non-destructive. There is no need to dissolve solids, press pellets, compress the sample, or otherwise alter its physical or chemical structure. This makes Raman spectroscopy ideal for investigating physical properties such as crystallinity, phase transition, and polymorphs. The lack of sample preparation also minimizes cleanup and the possibility of cross-contamination. Raman spectroscopy also has several advantages. Unlike other vibration techniques, its operational wavelength is usually independent of the vibrational modes being studied. Since Raman spectroscopy measures the shift in frequency from the excitation laser, it can be performed using any operating range from UV to NIR. It thus permits access to vibrational mode information normally associated with the wavelength ranging from 2 to 200 micrometer. This makes Raman ideal for the study of inorganic materials that have vibrational frequency in the far IR that are otherwise difficult to reach. Two techniques on which Raman spectrometer are based: Dispersive Raman and Fourier transform Raman. Each technique has its unique advantage and each is ideally suited to specific types of analysis. Dispersive Raman microscope using visible excitation wavelength deliver 1 micrometer spatial resolution and is widely used in the analysis of micron level sample contaminants. We will talk about Dispersive Raman or FT Raman. What is it actually? The resulting spectral information obtained is generally the same for both techniques. As a general rule, the main advantage associated with FT Raman is its absence of fluorescence interference. In addition, if the user already processes an FTIR spectrometer, it is frequently convenient and economical to add an FT Raman spectrometer to the unit. Since Dispersive Raman operates at the visible wavelengths, the Raman signal is much stronger. The technique is more sensitive and it delivers higher spatial resolution. This makes Dispersive Raman the best choice for small particles and minor component analysis. Typical Dispersive Raman applications. Dispersive Raman spectroscopy has been applied to many types of samples. Micron level spatial resolution combined with the ability to do confocal analysis and with the higher sensitivity obtained at visible laser wavelengths makes this technique ideal for minor components analysis, defect analysis, sample inclusion, and failure analysis applications, etc. Dispersive Raman is also widely used within the pharmaceutical and life sciences. Increased emphasis on single crystal studies is best met with Dispersive Raman. Dispersive Raman spectroscopy is an excellent technique for comprehensive polymorph screening during drug development, inorganic analysis, and sample identification in geology and gemology. More commonly use Dispersive Raman. Because this method avoids the metal oxide fluorescence that may occur with FT Raman spectroscopy. Confocal analysis is an excellent way to probe inclusions, gems, and semi-precious stones. This information can sometimes be used to identify the point of origin of these samples. Polymer laminates, layered paint samples, and other samples in which depth or cross-sectional information is desired are prime candidates for confocal analysis with Dispersive Raman microscopy. So students, let's summarize all the content that we have studied today. When incident light is scattered from a crystal or molecule, most of the photons are elastically scattered. The scattered photons possesses same energy and therefore wavelength as the incident photons. However, a small fraction of light, which is nearly 1 in 10 to the power 7 photons, gets scattered at optical frequencies different from, and which is usually lower than the frequency of the incident photons. This process, which leads to inelastic scatter, is termed as Raman effect. Change in rotational, vibrational or electronic energy of a molecule can cause Raman scattering. If the scattering is elastic, the process is known as Rayleigh scattering. If the sample being studied is irradiated by monochromatic light, for example from a laser, the recorded spectrum of scattered light consists of a strong line of same frequency as the incident light with weaker lines on the either side, shifted from the strong line by frequency ranging from a few to about 3500 cm inverse. Those lines of frequency which are less than the exciting lines are called Stokes lines, and the other termed as anti-Stokes lines. Samples can be investigated either in bulk or in microscopic amounts over a wide temperature range and physical forms, that is liquid, gases, powders, latex, monolayers to multilayer films, fibers, or as surface or embedded layers can be studied. Raman spectroscopy is for symmetric vibrations in nonpolar groups, while IR spectroscopy is best suited for the asymmetric vibrations in polar groups. A complex molecule can absorb and emit energy when interact with photons that can excite molecules to higher vibrational states. These quantized vibrations are called normal modes of vibrations of the molecule. A linear molecule having n atoms has 3 and 5 normal modes, which is a non-linear molecule has conversely 3 and 6 normal modes. Each normal mode can be identified by 3 motions. Bending motion occurs when 3 atoms connected by 2 bonds. Stretching motion, amid of 2 bonded atoms. Out of plane deformation modes that change from planar structure to non-planar one. Thank you.